Welcome to Chem Help ASAP. This is a reaction video to a NileRed video about extracting urea from pee. This is an older video from NileRed, but I think everybody will enjoy it. So let's see what NileRed is up to.
Urine's produced by the kidneys, and it's a way for the body to get rid of excess water and water-soluble waste. The exact composition of urine varies from person to person, but in general, this is what it contains. Not counting water, the largest component is urea, which mostly comes from the metabolism of food proteins. However, some of it's also generated naturally as the body degrades and recycles its own proteins. For this video, I've decided to continue this month's apparent theme of urine chemistry, and I'll be isolating some urea from my own pee.
Darn. Let's not stop there. Let's roll back just a bit. It was apparently urine month, and I missed it. This video is a little older, 7 months old, but I missed, the pee month in NileRed's calendar. I do like this is an older video. Look, he's in a kitchen. He's not in his lab. He's got so far to grow from here. It's exciting to see.
Theme of urine chemistry, and I'll be isolating some urea from my own pee. Then, in some future videos, I'll be using the urea to make an old, now banned artificial sweetener, as well as an anti-seizure medication.
This is interesting. So I'm familiar with dilantin on the right, but this dulcin, I've never heard of this compound, not familiar with it as an artificial sweetener. So that's interesting to me as an organic chemist.
Using something that was once part of me to make new chemicals is honestly kind of weird, but I also think it's pretty cool. I should make it clear, though, that unless you're living in some sort of post-apocalyptic world, this is probably the worst way to get urea. It's way easier and cheaper to just buy it or to get it from some instant cold packs.
So let's take a quick break here because I want to talk a little bit about urea, because urea is actually a really important compound in organic chemistry. Urea in organic chemistry. So the first reported synthesis of urea in a lab was by Friedrich Wohler, and that was in 1828, almost up to the bicentennial for this urea synthesis. And what was important is he made it from inorganic substances. Now, many organic chemistry textbooks will reference this synthesis in like the first chapter of the text, and will kind of credit this as being the start of organic chemistry. That might be a stretch, but it's certainly the start of maybe synthetic organic chemistry. This discovery was important because it worked against the idea of vitalism, and there is an idea that organic chemicals can only be made by living organisms. And because Wohler did this from inorganic substances, it wasn't. So that struck against vitalism. That's a big deal scientifically. So nitrogenous waste in the body, this does arise mostly from protein degradation. And the problem is protein degradation, proteins are made of amino acids, and the amines in amino acids, specifically ammonia, it is kind of toxic to the body. Now fish don't have to mess with this because they are bathing in water, so they just constantly excrete their ammonia, and it's not an issue. But in mammals like us, it is a problem. So what we do is we convert the ammonia to urea, and you can see urea up here. Urea has two nitrogens. It can bind together two molecules of ammonia in a non-toxic form. It's water soluble, and so when it's convenient for us, we can just pee it out and excrete it in our urine. Now, not all animals have the luxury of carrying around all this water as urine, as weight, and that's like birds. And so those animals will convert their ammonia ultimately into uric acid. And uric acid is shown over here on the bottom left. And uric acid contains 4 nitrogens. And you can kind of see 2 urea molecules tied up together here. And this is also non-toxic, but it's excreted through the feces of these animals. So bird poop contains uric acid. And that's the bird's way of safely disposing of this toxic ammonia nitrogenous waste.
Just doing it to explore the science, and despite it being honestly pretty gross, I think it might be fun. Anyway, to get the project going, I had to start saving all my pee in a container, which was not super enjoyable.
That urine looks terrible. Oh my goodness. Somebody call a urologist. That looks rough.
It took about 3 days to collect a little over 3 liters of the nice golden liquid. Most of it's just water though, which I'll need to get rid of before trying to isolate the urea. Unfortunately, the best way to do this is by evaporation, which is really stinky. Because I didn't really want my house to permanently smell like pee, this step had to be done outside.
Had to be done outside, Again, there's no laboratory. Let's just go outside and do this.
Picked up a large pot from Walmart, added all the pee, and then heated it up on a small electric burner. I also set up a fan off camera to continually blow on it and speed things up. As the pee is heated, proteins and minerals will start to fall out of solution, causing it to become opaque. The urea is extremely water soluble though, and will remain dissolved.
So you reduce the volume, things that are less soluble, which is not what he wants, that'll fall out of solution, and things that are more soluble like the urea will stay in solution. So he's getting rid of water, and by filtration he'll be able to get rid of these solids that fall out of solution.
The goal here is to get rid of almost all the water until I get to
That looks disgusting. That is cooking pee. You know that's horrific.
a volume around 150 to 200 milliliters. Surprisingly, at the beginning it really wasn't that smelly, but it slowly got worse and worse.
That was surprising. Surprisingly, it got worse and worse.
By the time that it was done, it absolutely reeked and was very unpleasant. While holding my breath, I quickly took it off the burner and poured it all into a beaker.
Okay, so he went from, what did he say, about 3 liters or so of urine, and now he's down to a concentrate that's less than 200 milliliters. So that's, okay, it's definitely concentrated a lot.
Covered it with some plastic wrap and brought it inside to cool. This wasn't the greatest idea though, because even with the plastic, the smell was easily able to pass through.
I'm amazed at how dark it is. I mean, yes, it was dark beforehand and now it's been concentrated, but it really is. I mean, it's like coffee colored. It's super dark. He does have solids in there though.
It didn't stink up the whole room, but it was definitely a little gross in the area around my workbench. When it eventually cooled to room temperature, I vacuum filtered off the solid stuff. As I mentioned before, this is a mixture of proteins, minerals, and other pea components.
You know, I don't think there should be much protein in there. Typically having protein in your urine is a sign of kidney issues. So I hope he doesn't have any protein in there, but there are certainly other things dissolved in urine that he's going to concentrate and precipitate out.
I waited for everything to pass through, and then I washed the beaker and the filter with a little bit of water. In the flask below, I have all the liquid that passed through the filter, which is extremely dark and nearly black. This extremely concentrated pea contains all the urea, and to get it out, I'm gonna have to chemically process it. To do this, I transfer it all to a beaker and start adding concentrated nitric acid. This reaction produces a lot of heat and it can easily get out of control, so the acid has to be added slowly with a lot of mixing in between. The nitric acid quickly reacts with any urea that's present to produce urea-nitrate, which is not very soluble in water.
This is surprising to me. I tend to think of almost all nitrates as being very water soluble, but of course those are metal nitrates. Aside from, metal nitrates in general are very water soluble. But here's an organic nitrate, urea nitrate, and it's insoluble. This is very surprising to me.
The pure form of urea nitrate is white, but unfortunately, as it precipitates, it picks up a lot of colored impurities. So,
look, it totally does. It precipitates. Let's talk a little bit about why this might precipitate. Okay, again, this complex, this solid precipitate from urea and nitric acid is kind of fascinating. So I'm just going to draw on this. So here is urea, and it is protonated on the oxygen. And something about this, it is insoluble. Well, with nitric acid, you could imagine forming some interesting hydrogen bonding interactions between the nitrate anion and protonated urea. And these kinds of interactions are exactly what's seen in double-stranded DNA, where you have this Watson-Crick base pairing interactions. And so then you can imagine this could continue to interact with another urea molecule. Protonated urea, and then this could continue down. So we can now just repeat this pattern. And you can see that this could just continue on as kind of this long string, and maybe even you could have more interactions off the face here with other nitrates. So, this all of a sudden, there is something special potentially about nitric acid and protonated urea, which wouldn't happen with other common acids like HCl couldn't do this, sulfuric acid probably couldn't do this. So there's something special about nitric acid in forming these insoluble crystals with urea.
So it ends up being a dirty brown color instead. It also puffs up a little and makes some nice and appetizing pea foam.
Okay. Pea foam. Nice. I think the foam is probably related to acidic hydrolysis of the urea. If you hydrolyze urea, you make carbamic acid, and carbamic acid is not stable. It releases CO2. That would be as bubbles. It makes CO2 and ammonia. So I suspect there's a fine balance between getting precipitation and having some background degree of hydrolysis of the urea.
This is probably the major thing to look out for with this reaction, because if it ends up overflowing, it's not going to be very fun.
Listen, this is always a hazard. Anytime you generate gas in a vessel like that beaker, it's got nowhere to go but up. And if you generate enough bubbles, then it's going to overflow. And so gases in organic reactions are a pain because most vessels either get narrower at the top or they're just straight walls. So we'll see that at least one more time in this video.
Besides the foaming, the reaction was relatively tame, but it did warm up quite a bit. So to precipitate as much urea nitrate as possible, it needs to be cooled. I continue mixing it for a few minutes, then cover it with some plastic and put it in the fridge for a couple hours. At this point, it still really stinks though, so I tried triple bagging it to save my fridge. The smell still leaked out a little, but it wasn't too horrible. A few hours later, I took it out, and the whole mixture had solidified.
Okay, that's pretty cool. So this is apparently pretty darn concentrated with urea, or this nitric acid salt of urea, because if the whole thing's solidified, and you can see in the bottom, it is looking thick.
What I need to do next is filter it, so I quickly break it up using a glass rod. Then all of the gross brown goo is added to a vacuum filter. I turn on my pump, and most of the dark, concentrated pee is pulled out. It's all collected in the flask below, and thankfully, it can now be discarded. This is where all the stink is coming from, so from this point on, things are going to be a lot more pleasant.
Again, I'm kind of blown away that you can form this insoluble complex between nitric acid and urea to get a non-water soluble solid. Urea is water soluble, nitric acid is certainly water soluble, most nitrates are water soluble, but urea and nitric acid together are insoluble in water or poorly soluble in water. That's interesting.
I left the pump on for several minutes just to dry it up as much as possible, and then I transferred it to a beaker. Although the urea nitrate doesn't stink that much anymore, it's still super brown and gross, so I'm gonna clean it up a little.
I think he's being a little harsh. That is, he clearly got a lot of the color out when he filtered it in that center glass funnel. So this is, our eyes pick up color, and so we're very sensitive to color. But I suspect the amount of brown impurity in there it is not as much as the way it looks on that solid.
The easiest way to do this is to recrystallize it from hot dilute nitric acid. So I turn on the heat and I just keep adding the acid until everything dissolves.
I kind of wonder what the concentration is of that nitric acid. Are we talking 1 molar, 10th molar? Is it kind of concentrated or truly dilute?
Then I take it off the hot plate and remove the stir bar. As the solution cools to room temperature, the solubility of the urea nitrate will decrease and it'll start to crystallize out.
Okay, that's beautiful.
Of the urea nitrate
See it
will
again.
decrease and it'll start to crystallize out.
How about one more
Start
time?
room temperature, the solubility of the urea nitrate will decrease and it'll start to crystallize out.
Recrystallizations, I don't care how long you've been in lab, when a recrystallization gives a dynamic change like that, even though it's likely a time lapse, it is fascinating. It's just incredible to watch. What he's seeing here is where he has so much solid forming that it's actually entrapping, and let me tell my lights I'm still here, it's actually entrapping the liquid within the crystal lattice. So it looks like there's no liquid left, but there's plenty of liquid in there. He's just got to poke it around a little bit, but that's captivating.
To fully crystallize everything, I again put it in the fridge for a few hours. Then I take it out, break it into smaller pieces, and filter it off.
So by breaking it up, that frees some of that liquid that's trapped inside and between all these intertwined crystals.
The crystals here still aren't perfectly white, but it's definitely a lot better than before.
Oh yeah.
When everything's been pulled through, I wash the beaker and the crystals a couple times with some ice-cold dilute nitric acid. Then I leave...
So he's using nitric acid just to maintain the low pH, to make sure his urea stays protonated. And of course he wants it to be cold because that reduces solubility. So acid and cold.
The pump on for several minutes to dry things up as much as possible. What's really nice is that from this point on, the prep is much more pleasant because the urea nitrate I have here is practically odorless. Anyway, now that I've separated and purified the urea nitrate from the gross urine,
so just by eye, that looks like a pretty good amount of solid. That's impressive.
I need to change it back into urea. To do this, I dump it all into a beaker and I suspend it in a small amount of water.
So, as I watch this, so he's adding water, he's going to do some chemistry here, but, look at that hot plate. That hot plates, these ceramic hot plates, they always take a beating. Even if you're careful with them, they're going to get dinged around, and that's got a nice chip in the middle. That tells you that hot plate has done some work, and so it's served a useful life.
Then I slowly start adding a concentrated solution of potassium carbonate. It reacts with the urea nitrate to regenerate urea, but it also forms potassium nitrate and carbon dioxide gas as side products.
Oh boy, carbon dioxide gas. Here comes the fizzing, always a pain to deal with, and we're in a straight wall vessel.
So immediately, a whole bunch of bubbling occurs, and I realize that doing this in such a small container is a horrible idea. To prevent a disaster, I quickly transfer it to a larger one and continue the addition.
So, this is still a straight wall vessel, but it's a lot bigger, and so he's going to have enough volume to capture all those bubbles, not have them fizz out. But this will consistently catch you by surprise in lab. Daggone it, it's bubbling. What am I going to do?
The goal here is to just keep adding the potassium carbonate until all of the solid urea-nitrate disappears. The urea that forms quickly dissolves, and I'm eventually left with a nice and clear solution. It's still really discolored though, so I tried seeing if activated charcoal would help.
Activated charcoal is the classic way to get rid of colored impurities. In my experience, it never works. It's always a disappointment. It really depends on what is the source of the color. Certain types of colors and dyes, highly conjugated aromatic rings, those tend to work better with activated charcoal. But in my experience, when I've thought, oh great, I'll add some charcoal and it'll be such an elegant, quick way to get rid of the color, I'm always disappointed.
It usually works pretty well, so I mixed in a small amount. Then, to get rid of the charcoal, I filtered it through some cotton and sea light. Unfortunately, it turned out to be a total waste of time though, because there was no noticeable color difference.
Yeah, that is my experience with charcoal almost every time. I don't even try anymore.
In any case, I now need to evaporate all of the water. So I quickly set up a hot water bath and a fan like before. It's really important to not heat it up too much here, and definitely not to boiling, otherwise some urea might start to degrade.
Okay, this is interesting. So in the past, he's just been heating this thing on the hot plate, but now he says he's got to be careful because he doesn't want to degrade the urea. How can he be more careful? Instead of heating his beaker directly on the hot plate, he puts a water bath on the hot plate. So that water bath is going to absorb the heat. He's going to heat the water in the bath, and then that water will heat his beaker. As a result, he's not going to be able to get his beaker any hotter than 100 degrees, the boiling point of water. So it really, it served, that water bath serves as a mediary because that hot plate can get darn hot, hundreds of degrees Celsius, but it's protected from extreme heat by that water bath.
The process took a few hours, and I was eventually left with a thick syrup. As soon as it was taken out of the water bath, it quickly started to solidify. I let it sit there for another 20 or 30 minutes, and it became a solid chunk.
That's impressive, because, I know that's not a huge volume of solid, but if that's a solidified mass, that's pretty good amount of material.
What I have here is a mixture of potassium nitrate and urea, which I'll have to separate. To do this, I'll exploit their differences in solubilities, where urea is very soluble in hot ethanol, but potassium nitrate is practically insoluble.
So he has an inorganic salt and a small, highly polar organic molecule. So it's not surprising there's a window of solubility difference there where you can try to exploit that and get these things apart based on their solubility.
So by adding boiling hot ethanol, I should be able to pull out the urea, but leave the potassium nitrate behind. I add a small amount and mix it around to break up all the large chunks. It looked pretty good after a few minutes, and I was gonna go ahead and filter it. However, at the last second, I decided to add more ethanol. At the last second, when you're doing these separations and these recrystallizations, you're never 100% confident. There's always some guesswork, and it just, maybe I'll do this, and because you don't want to take a step that's irreversible because you can't take it back. So I'm not going to filter it. I'll just give it a little more ethanol. But it is a guessing game, and you're going by feel, and you can't develop that feel until you do some reactions and you mess them up. And I think NileRed has probably messed up some reactions. So I was like, this doesn't look quite the way I expect. So let's give it a little bit more solvent. I did a random amount that I felt was appropriate.
A random amount that I felt was it's not random. He's going by his intuition. He's managing his expectations and just going by the seat of his pants. But that's what you got to do sometimes.
Mixed it around for about 30 seconds and then filtered it. By the time I was done, a lot of solid had formed, which I initially assumed was urea. I figured that because the ethanol was cooling down, the solubility of urea decreased, and some of it fell out of solution.
That's a totally reasonable a line of thinking, and nothing wrong with that at all.
The next step is to heat things up and evaporate off the ethanol, and if this is urea, it should redissolve. However, even when it got to the boiling point, it was still really cloudy, so this is probably potassium nitrate. I get rid of it by just quickly filtering it through some cotton, and the difference is pretty significant.
Okay, let's just go back and see the difference.
Quickly, so this is probably
Cloudy.
potassium nitrate. This is pretty significant.
Filtered. That's different.
Anyway, I continue evaporating off the ethanol, and when it gets to 100 milliliters, I transfer it to a smaller beaker. Then I evaporate further another 20 mils or so the total volume is around 80 milliliters. At this point, I take it off the heating, remove the stir bar, and wait for it to cool. The crystals that form first are...
So he transferred this to a smaller beaker. Why would he do that? Well, he knows he's not going to have massive amounts of material. And so he's just getting it when it's in a dissolved liquid form into a smaller beaker because that's convenient to transfer, as opposed to forming a solid in this massive beaker where he's got to try to scrape off all these surfaces to get his solid. So you keep your material as concentrated as possible.
Very needle-like, and I think it's actually potassium nitrate. As it cools more though, we start to see some lighter and fluffier crystals, which I think is the urea. When it eventually got to room temperature, I put it in the freezer and cooled it overnight. Then just like...
Again, that was just a beautiful progression, these little facets forming and reflecting light through that liquid and falling off the sides of the glassware. It's fun to watch when you see your product coming out of solution like that.
Like we've seen before, I break everything up and filter it off. After everything is pulled through, I wash it a couple times with some ice-cold ethanol to try to get rid of the color. It seemed to get rid of some of it, but it was still quite yellow, which okay, it is yellow. Objectively, that is yellow. But man, this looks so much better than it used to. It's really improved. I didn't really like. This yellow color is mostly due to a pigment called urachrome, which comes from the breakdown of hemoglobin. It's generated pretty consistently by the body, and it's the reason why pee is yellow.
I think it's also the reason poop is brown too. So that color it goes out multiple ways.
Anyway, to get rid of the urachrome and any potassium nitrate that still might remain, I just need to recrystallize it a few more times from a mixture of water and ethanol. On the last run, nothing crystallized even when I put it in the freezer, which kind of scared me. This does happen sometimes though, and crystallization just needs to be induced by scraping the wall a little.
Let's just watch that again. It's beautiful.
Put it in the freezer, which kind of scared me. This does happen sometimes though, and crystallization just needs to be induced by scraping the wall a little.
Just that agitation between the glass stirring rod and the wall of the beaker. That's amazing.
To finalize the crystallization, I put it back in the freezer for a couple hours. Then, as usual, I broke it up into pieces and filtered it off.
You can see there again, it looks like a solid mass, but once you start to chop it up, that releases any solvent that's trapped between the crystals.
I turned on the vacuum pump, and I was really happy to see that most of the yellow color quickly disappeared. Then I did a couple washings with some ice-cold ethanol. The final crystals are still slightly yellow, but it's definitely way better than before. I let it dry overnight and the final mass was about 7.8 grams. I have no idea how much urea I actually had in my pee, but I imagine this is a really low recovery. From my research, it seems like there should be at least 9 grams per liter, so minimally, I should have gotten around 27 grams. It is possible that I have some sort of condition or disease that makes me make really low amounts of urea, but I choose to believe that it's because of all the recrystallizations.
Hey, that is not bad. So maybe the maximum yield is going to be 30 grams and he got 7 grams. I think that's a huge success.
Some product is lost with each recrystallization, so it's kind of a trade-off between recovery and purity. In my case, I'm using it for synthesis, so it has to be reasonably pure, and I didn't really have a choice here. If you recall from earlier, I filtered off some pea proteins and minerals, and I decided to keep them.
Those pea proteins and minerals, again, I don't think there's probably not much protein in there.
I let them sit out for a few days to dry, and this is what I was left with. I have no idea what I can actually use it for though, so if you guys have any ideas, I'd love to hear them in the comments. Anyway.
I don't want to hear what those ideas are. I bet some of those ideas are crazy.
One final thing that I did was test the purity of the urea. To do this, I measured its melting point, and I got a range of 120 to 135 C. This is kind of close to the melting point of pure urea, but the range is much wider, which tells me that mine is still quite contaminated.
It could be. I gotta say, those crystals look pretty nice. And what could be the impurity? Maybe a little bit of potassium nitrate? For his purposes, what he wants to use this material for, fortunately, that potassium nitrate will not cause any problems. So I think this is going to be really, really good for material for subsequent reactions.
This is fine for my future videos though, and the reason I know this is because I've already filmed them.
Spoiler alert, come on, man.
Both of them should be posted later this month, and if you're interested in seeing them, you should definitely subscribe and turn on notifications.
Okay, let's go back to a picture. There we go. Listen, that was a great video. Thank you, NileRed, for sharing this part of P Month with everybody. And always a fan of your work, and I know a lot of people enjoy your content. As for you, thank you for watching all the way to the end. If you have any comments or feedback, please let me know. If there's any video you'd like to see in the future, please let me know that as well. Anyway, take care.